In lesson 5.5, we're talking about limits at infinity and limits of sequences. Our two big theorems for limits at infinity is if we've got the variable in the denominator, so 1 over x, and it doesn't matter what the exponent is. If we are taking x to infinity, then the answer will be 0. And so what we're seeing here is if we take a number, any number, divided by infinity, then the number is going to be so small that it's basically 0, so it's headed to 0. And it also doesn't matter if we're headed to negative infinity, it's still going to be 0 because we're dividing by such a large negative number. We can see this in a table. If we've got the function 1 over x, and we take x to be really, really large, we see that the values get really, really small. So when we do 1 divided by 1, it's not that small. Then 1 divided by 2, it's smaller. 1 divided by 4, 0.25 is smaller. 1 divided by 10 is 0.1. 1 divided by 100, 0.01. 1 divided by 10,000, we've got 0.0001. And so already 10,000, that's not even close to infinity, and we've gotten the answer down to something so small that it's 0.0001. So we can also see that in the graph that pretty suddenly, as the x values get big, the y values get really, really small. So if we're going to take x to infinity, we can say that the answer is going to be 0, or the limit would be 0. So in example 1, we're evaluating the limit. It says find the limit, and here we're taking x to infinity. So we go ahead and we can use direct substitution here. So if we plug in infinity, we're going to have 4 minus 3 divided by infinity squared. And then infinity squared is just a bigger infinity. And so then we get 4 minus a number divided by infinity. We just said with those theorems at the top equals 0. So the answer is 4 for example 1. In example 2, the rule here is going to be divide by the largest x value on the bottom. So what this is going to do for us is going to create little fractions that we can find the limit of, and we're going to find the limit of each fraction and be able to find the total answer. So the biggest x on the bottom here is x squared. So we are going to divide by x squared on the bottom, or multiply by a 1 over x squared. If we do that to the bottom, we have to do that to the top. So that is going to create negative 2x over x squared plus 3 over x squared for the top, and then 3x squared over x squared plus 1 over x squared for the bottom. Then we go ahead and simplify that where we can. So that's going to give me one of the x's cancels, so negative 2 over x. Nothing's canceling on the 3 over x squared. And then these x squareds cancel, and I've got 1 over x squared. From there, we can fill in our infinity. So we're going ahead and plugging in infinity. So I'm going to have negative 2 over infinity plus 3 over infinity squared, which is infinity. And then 3 plus 1 over infinity squared, which is infinity. And from the rules at the top of our notes, we see that a number divided by infinity is 0. So that is 0. 3 plus 0. So we get 0 over 3, which is 0. So part A's answer is 0. All right, part B, the biggest x on the bottom is x squared again. So we're going to divide by x squared, or in other words, multiply by 1 over x squared on top and on bottom. And so that gives me negative 2x squared over x squared, 3 over x squared, 3x squared over x squared, and 1 over x squared. And then we're going to go through and simplify that. So these x squareds cancel. This 3 over x squared does not reduce. On the bottom, the x squareds cancel, and the 1 over x squared does not reduce. And then we go and we plug in our infinity. So we're going to have negative 2 plus 3 over infinity squared, 3 plus 1 over infinity squared. And so we get -2 plus a number divided by infinity is so small that it's basically 0. And then I've got over 3 plus 1 divided by infinity, so another 0. And so my answer here is -2/3. For C, we've got x squared again on the bottom. So we're going to divide by x squared. So that's going to be -2x cubed over x squared, 3 over x squared, 3x squared over x squared, and 1 over x squared. Then we go through and we simplify that. So the x squared will cancel. We're going to have -2x. Then 3 over x squared does not reduce. These x squareds cancel. And I've got 1 over x squared that does not reduce. And then now we can plug in our infinity for all the x's. So I'm going to have -2 times infinity plus 3 divided by infinity squared over 3 plus 1 divided by infinity squared. So -2 times infinity is infinity, negative infinity. Then I've got 3 divided by infinity, which is 0. Then I've got 3 plus 1 divided by infinity squared, which is 0. And so I have negative infinity divided by 3. And if you think of a really, really large number divided by a positive number, you get then negative infinity. And since we can't actually reach infinity, we would say the limit does not exist. Now, if you think we've talked about this before, we have. This was before we ever talked about limits, but we saw the same sort of things happen when we talked about asymptotes. So the rules for asymptotes are really the same as these infinity rules for rational functions. So if we've got a polynomial divided by a polynomial, which is a rational function, we can just look at the leading exponents, or the degree of the top and the degree of the bottom. So here, x to the n, this would be degree n, and then x to the m, this would be degree m. So if the top degree is smaller than the bottom, which is what it's saying right here, if the top degree is smaller than the bottom degree, then the answer will just be 0. The limit when you go to infinity will be 0. If the top degree matches the bottom degree, if n equals m, then you're just going to have your leading coefficient, that a divided by b, in front. And then if the top degree is larger than the bottom degree, if n is bigger than m, then the limit will not exist because you're going to end up getting infinity as an answer. In example 3, you're finding the average cost. You're manufacturing a product that costs 50 cents per unit to produce. Your initial investment is $5,000, which implies that the total cost of producing X units is given by this function. The average cost per unit then is the cost divided by how many units you are producing. So you would take that function divided by X. It wants us to find the average cost per unit when we have the following units. So when we look through here, you're manufacturing a product that's 50 cents to produce. So that would be like the cost of materials for it. And your initial investment is 5,000. So that would be like the building and the machinery or the employees. So that's whatever's going into it. And then this would kind of be the materials. And so if we have this fixed cost of 5,000, we can't get rid of that. If it costs 50 cents to produce, we can't get rid of that. But the more products we make, the more profit we can make. And we'll kind of look and see why that works. So what we're going to do is plug in 1,000 and see what the cost, the average cost would be. So we've got, if x is 1,000, we're going to plug that in. And we end up getting $5.50. And that is how much each product on average is going to cost us. So that takes into account that it's 50 cents to produce each product, And then we've got that 5,000 that we've got to split amongst how many products we're making. So let's say that we wanted to sell our product for $10, then here we are making $4.50 profit, which is good. But what if we want a better profit than that? So what if we can make 10,000? So what if we can up our production to 10,000 units? We plug in 10,000. And we see here that really lowers our cost down to $1. So if I'm selling my product for $10, now I've just made $9 profit on each unit that I've made. Well, then why stop at 10,000? If we can make more, then let's try it. So let's try 100,000. And so when we plug in 100,000, we get it down to 55 cents. So now we're making a lot better profit. But we want to know, so here the profit or the average cost jumped down really fast. But from here to here, it's not jumping down as fast as it was. So there must be some limit to how far down we can take this average cost. So if we want to know the limit to it, then let's go ahead and take the amount of units to infinity. So let's say, so x is units, that we're going to take the number of units to infinity and find out the most true limit to how much we can take down the average cost. So we're going to have 0.5x plus 5,000 all over x. And so what we'll do then is divide by the biggest x on the bottom, 1 over x. And so then that gives me the limit as x approaches infinity of 0.5x over x plus 5,000 over x all over x over x. Then we go ahead and simplify that. So these x's cancel. Then we've got 5,000 over x, that doesn't reduce. And then we've got x divided by x, which is 1. And then we can go ahead and plug in infinity. And so we're getting 0.5 plus 5,000 divided by infinity is going to be 0 over 1. So this tells me that the lowest I can get my average cost to is 50 cents. So if we're already at 55 and that's working for us, then we don't really need to go that much higher than 100,000. But really 50 cents is going to be our lowest that we can get our cost down to.